Hello and welcome back once again to this lecture series on aluminum based alloys and metal matrix composites. So, in the past few lectures we have discussed about grain refinement by melt inoculation. So, we have seen that in this process of melt inoculation, a grain refiner is added into the melt, and this refines the grain size by providing the heterogeneous sites for nucleation. Okay. And then we have discussed different theories of melt inoculation to understand the mechanism of grain refinement in this process. And then we also talked about what is called fading and poisoning. And discussed the reason behind their occurrence as well. Okay. So, we have discussed all that with regard to melt inoculation. But in the liquid metal, apart from addition of such inoculants, you can take the help of some other mechanisms also through which the grain size can be refined, and vibrating or agitating the melt is one such mechanism through which the grain size can be refined during this melting and casting process. Okay, so that is what we are going to talk about right now. If you remember this, I had mentioned this before briefly, that the grain size during melting and casting can also be refined by agitating the melt by physical stirring with the help of a mechanical stirrer or some other means such as ultrasonication or electromagnetic stirring and so on. So today we are going to learn about the mechanisms as to how exactly the vibration or stirring of the melt leads to the grain refinement. Okay. So as I said before, you can have different methods of stirring, such as mechanical stirring, where you can use a mechanical impeller, dip it into the liquid melt in the liquid metal, and then stir it with the help of an external motor. Okay, so you fix your impeller with the help of a shaft to the motor and then dip it into the melt and start rotating it. Okay, so that will create enough agitation in the melt which can lead to grain refinement through certain mechanisms, as we are going to talk about right now. Then you can also do the stirring by electromagnetic means. Electromagnetic stirring will also lead to a similar effect of vibrating and creating agitation in the melt. And apart from that, you can also have bubble mixing for doing the same thing. Okay, so these are the different ways by which the liquid metal can be stirred, which will ultimately lead to a finer grain size. Okay, so let us look at the different mechanisms through which that occurs. The first one says that it occurs through a shear fracture mechanism of the dendritic arms, right? So we know dendrites are a general kind of structure that you obtain in casting. So dendritic structures are very common in castings, in metals, including aluminium. So here when you start the melt, by one of these methods, the shear force which is caused due to the stirring of this viscous fluid will lead to the breakage of the dendrites. Okay, and once that happens, these broken dendrites will be now dispersed into the melt and lead to grain multiplication. Okay, and this stirring could induce elastic and plastic bending of the dendritic arm as well. Okay, so that will also have some effect, this bending of the dendritic arm, and that is what we are going to see next, as to what is going to happen when you have the arm bending, the bending of the dendritic arm. So that could lead to the infiltration of the grain boundaries. So this liquid infiltration in the grain boundary is induced by the plastic bending of the dendritic arm. Okay, and this plastic bending is actually induced by the stirring of the melt. Okay, so when the grain boundaries achieve a misorientation of more than 20 degrees due to the plastic bending, then the grain boundary energy could exceed the energy of the solid liquid interface by 2 times, and if that happens, then the liquid can actually penetrate the grain boundary, because liquid penetration now will actually reduce the energy of the system, since the grain boundary energy is more than the solid liquid interfacial energy. Okay, so this penetration of the liquid into the grain boundaries will now detach the dendritic arms from the mother grains, and they will again fragment into smaller fragments and get dispersed into the liquid metal. Okay, so what I mean here, the penetration of the liquid into the grain boundary can be understood if you just have a look at this schematic over here, this diagram that I am going to draw. So let's say, between these two grains, you have this grain boundary. So this is a solid grain, and this is also solid. And in between them, you have the grain boundary. And it is actually nucleating from the liquid. So here you have the liquid. So now the surface tension of the liquid will form an angle here with the grain boundary. And this angle is known as the dihedral angle. So now if I only take the surface energies, it will be like this. So here you have the solid liquid surface energies, gamma SL, and this is the solid surface energy, or the grain boundary energy, and this is the dihedral angle. So if you take a simple balance of forces here, you would get this equation. right? So when the angle becomes very small and approaches 0, then you could see this will become 2 times the solid-solid interfacial energy will become 2 times the solid-liquid interfacial energy. Okay, and that's what I meant over here. If phi approaches 0, then gamma SS will be equal to 2 gamma SL. Okay, so when a condition like that prevails, then the liquid would penetrate the grain boundary, because that will reduce the overall energy of the system, right? Simply because the solid-solid interfacial energy is now more than 2 times the solid-liquid interfacial energy, right? So as it happens, as the liquid penetrates the grain boundaries of the dendrites, the dendritic arms could detach from their mother grains. Okay, but for this to happen, the relative motion velocity of primary phase and the liquid phase should be large enough, and that is why you need to start the melt vigorously by using one of these means, right? There is one more mechanism which talks about remelting of the dendritic root, which is induced by ripening and stirring. So we have seen that solute segregation can happen during solidification depending on the nature of the solute and the diffusivity and so on. And the segregation of these solutes at the dendritic root can lead to a decrease in the equilibrium melting point. Okay, and due to this decrease in the melting point, it can actually lead to a curvature, which can be expressed by this particular expression over here, where delta T is that difference or the decrease in the melting point due to the solute segregation. Okay, and the other parameters that you see over here, V is the molar volume of pure solid, sigma is the solid liquid interfacial energy, delta HM is the molar enthalpy of fusion, and R is the radius of curvature of the solid liquid interface. Okay, so the segregation of the solute would lead to a curvature in the interface, in the solid liquid interface. And the other thing that could occur due to this stirring is the strong fluctuations of temperature and composition, and the stress which is generated due to that, due to this curvature which is induced by this temperature fluctuation and also the composition fluctuation, that would lead to generation of stress which may get concentrated at the dendritic roots. Okay, and as a result of that, it will cause remelting of the dendritic root. Okay, this is a combined effect of stress and the decrease in the melting point due to the segregation of the solute. Okay, so it will now lead to the same phenomenon that we talked about before, that is detachment of these dendrite arms from the mother grain, leading to their dispersion in the liquid metal. There is one more mechanism known as crystal rain. As I would have mentioned before, the mold wall that you have can also act as a heterogeneous site for nucleation, right? Because that is also an additional surface which is being presented to the liquid metal when it is poured into the mold. So in the early stage of solidification, there is a large degree of undercooling on the surface of the mold, and therefore the solid crystals will form on the mold walls, right? Now we know that the density of the solid phase is higher than the density of the liquid phase, and therefore the nuclei, the solid nuclei which formed on the wall, will fall into the melt and lead to what is known as the crystal rain. Okay, so if you have looked at the microstructure, in a mold as to how the grains solidify in a mold, the solid grains, you would see that near the mold you have a high undercooling because the mold leads to a chilling effect, right? Here the heat transfer rate is much higher, the cooling rate is higher, okay? So therefore it will immediately nucleate the solid grains as fine nucleus grains along the mold walls. And if you go away from the mold wall, then it will take up those dendritic or columnar kind of morphology as the thermal gradient develops, right? Right. So this fine nuclei, this solid nuclei formed on the mold wall can get detached from the mold wall because of the density difference and get dispersed in the liquid. Okay, as if a lot of these are falling into the liquid, and that is why this phenomenon is known as crystal rain. Okay, so that will lead to creation of this suspended solid into the melt and increase the number of nuclei and hence lead to an increase in the nucleation rate. So these are the different mechanisms of grain refinement that is achieved by stirring or vibrating the melt. So apart from physical or mechanical vibration, this vibration can also be generated by other means, for example, by ultrasonic waves. If you expose the liquid metal to ultrasonic waves, it can create a lot of vibration into the melt and can lead to a mechanism which will refine the grain cells. Okay, so that process, that phenomena which occurs due to the ultrasonication of the liquid melt is known as cavitation, which is basically a process of formation, expansion, and collapse of bubbles in the melt. Okay, so this is through the creation of this kind of sequence of formation, expansion, and collapse of bubbles, which leads to the agitation in the melt, leading to the grain refinement. Okay, so the collapse of bubbles can produce high pressure on melt layers in a very short time and enhance the nucleation rate, and can also lead to dendrite fragmentation, both of which are conducive for grain refinement. Okay, we have seen before, higher the nucleation rate, finer will be the grain size, and just now we talked about the dendrite fragmentation, which leads to grain refinement. Okay, so this collapsing of bubbles due to the cavitation that is achieved by ultrasonication will actually lead to high nucleation rate and dendrite fragmentation, which ultimately will give rise to grain refinement. And the pressures can cause a decrease in the activation energy for nucleation. So that is again related to the nucleation rate. If the activation energy is reduced, then more nuclei will form in a given time, leading to a high nucleation rate. So that again comes by due to the fact that the pressure which is generated by this cavitation effect leads to a decrease in the activation energy for nucleation. And the pressure could be high enough to break up clustered particles as well as dendrite arms, leading to higher nucleation rate. So this is through another effect that leads to a high nucleation rate, that is providing more and more particles for heterogeneous nucleation to occur, right? Due to the creation of such high pressures. And bubble collapse can also increase the melting point of the melt near the broken bubbles, and therefore the effective supercooling degree is also improved. Okay, so all these factors, all these conditions created by the ultrasonication are actually conducive for grain refinement by various ways, either through a decrease in the activation energy or through an increase in the nucleation rate by having more heterogeneous nuclei in the form of these particles or the broken dendritic arms, or also in the form of a higher degree of supercooling. So here the grain refinement by ultrasonication occurs through this cavitation process, leading to all these phenomena. Then we also have this electromagnetic convection, which can be used to stir the melt. And here the magnetic field that you have is utilized. The magnetic field can induce a force which is known as the Lorentz force, and this will cause a pressure difference and intense convection in the melt. Okay, so here the stirring is created by a completely different mechanism due to the introduction of this Lorentz force as a result of the magnetic field which is present here. Okay, so in conventional casting, the melt first solidifies on the mold wall, as I was mentioning, and the nuclei will then grow into dendrites. Okay, but in the presence of the electromagnetic field, what happens is that the crystal nuclei on the mold wall could be swept away by the strong convection, right? So we have already understood how this convection is created due to the presence of the magnetic field in the melt, right? And now when the crystals are forming, the solid crystals are forming on the mold wall, they can be broken away or swept away by this strong convection and will be dispersed into the entire liquid metal, right? And this will increase the number of nuclei and would lead to a high nucleation rate, ultimately leading to grain refinement. Okay, so the process here, the process of grain refinement comes due to the presence of a magnetic field which induces a force leading to a pressure difference and creation of convection into the liquid metal. So this is another way of grain refinement in the liquid metal with the help of some forces that can create vibration or agitation in the molten metal. Okay, so let me summarize this particular method of grain refinement by vibrating and stirring the melt. First of all, there are different ways by which the stirring can be done, like mechanical stirring, electromagnetic stirring, and so on. And when you create the stirring in the liquid metal, there are certain mechanisms through which the grain refinement occurs, and that is what we have discussed in this particular class. Shear fracture mechanism, for example, leads to breakage of the dendrite arms, and when that happens, this dendrite is broken into smaller fragments and leading to grain multiplication. Okay, and the other way by which the stirring can promote grain refinement is through the creation of some kind of plastic bending in the dendrite arms, which leads to the penetration of the liquid metal into the grain boundary, and that in turn leads to the detachment of the dendrite arms from the mother grains. Okay. But for all this to occur, the velocity of the primary phase and the liquid phase should be large enough. So you need to start the melt quite vigorously. Okay. And then we talked about another mechanism which occurs through the remelting of the dendritic roots as a result of segregation of solute atoms, leading to a decrease in the melting point. Okay, and it also creates a curvature which develops a pressure on the solid liquid interface, and all these ultimately lead to the melting of the dendrite roots, leading to their detachment. Okay, and then we talked about this crystal rain, which is basically the nuclei which are formed on the mold wall getting detached and getting dispersed into the liquid metal, leading to more number of nuclei in the melt. Then we talked about two more methods of creating this vibration into the melt. One is through ultrasonication, which leads to cavitation, and this cavitation creates conditions in the melt which are conducive for grain refinement. For example, it leads to breakage of the dendrite arms, providing more nuclei, or decreases the activation energy for nucleation, leading to a high nucleation rate. So all these are good for grain refinement. Then finally we talked about this electromagnetic convection. Here the magnetic field is being utilized. The magnetic field creates a strong convection into the liquid metal, and due to that convection, the solid nuclei which form on the mold wall get swept away and get dispersed into the liquid metal, providing more heterogeneous nuclei and leading to grain refinement. So with this we come to the end of this lecture, but I will see you soon. Thank you for your attention.